Welcome back to math. We're on section 8, inequalities. We'll show inequalities on a number line, and we'll talk about solving inequalities. An inequality is a lot like an equation, but there's one big difference. Equations have an equal sign, which means that both the right and the left have the exact same value. Inequalities have a greater than or less than sign, which indicates whether the right or the left side has the larger value. So this sign means greater than, and this sign means less than. There's a lot of ways that people remember that, but the greater than sign points to the right, which on a number line is where values increase. The less than sign points to the left, which is the way on a number line that the numbers decrease. So we can say that 8 is greater than 5. We know that's true. 8 has a bigger value than 5. 8 is more than 5. Or we can say that 3 is less than 4. We know that's true also. We can combine the greater than and less than signs with an equal to sign. We show just one of the dashes of the equal sign. So this symbol means greater than or equal to, and this means less than or equal to. So we can say that x, an unknown, is greater than or equal to 10. That means that any value that's more than or equal to 10 makes x true. So, for example, it could be 11, 12, 13, 14. It could be exactly 10 because it has the option to be equal to 10. It could be 10.1, 10.001, 10 and a half. Anything that's greater than or equal to 10 will make x true. We can show inequalities on a number line as a visual solution. So let's talk first about the endpoints. The endpoint is the point where that range of numbers begins. If it's an open circle, it means greater than or less than. It means that that endpoint is not included. But if it's a closed circle, it means greater than or equal to, or it could mean less than or equal to, because that endpoint is included. Once we know where the endpoint is, we shade the part of the number line where the values are included. So let's do some examples. We have 4 number lines here. They all have the numbers 1, 2, and 3. Notice that on number lines there's arrows on the ends. That means that the numbers can continue forever and ever, upwards and downwards. If we want to show the values where x is greater than or equal to 2, so we're talking about 2, and it can be equal to 2, so we're going to show a solid filled in end line, and it's going to go greater than. So we're going to shade in all these values to the right, and that is where all the x's can be greater than or equal to 2. If we want to just show that x is greater than 2, it looks a lot the same, except that end point is not filled in. It's an open circle, and then we still shade to the right because these numbers are bigger than 2. Okay, for x is less than or equal to 2, again we're looking at 2, and it can be equal to, so we're going to have a filled in endpoint. Now these values are less than, so we'll go to the left, where numbers, the values go down, they're less than 2. And finally, x is less than 2. We're not going to fill in or shade that point because 2 can't be included in the solution, but x, all the numbers, x can be all those numbers that are less than 2. Inequalities can have a compound solution when the two inequalities are joined together with either the words and or the word or. We'll talk first about and. So if we join two inequalities together with and, we call it an intersection. It means that both inequalities have to be true. So let's consider x is greater than or equal to -2 and x is less than or equal to 2. We'll start with this one. x is greater than or equal to negative 2. I've got a number line. We've got 0 in the middle, the negative number's going this way, the positive number's this way. We're looking at negative 2, and it can equal negative 2, so I will have a solid endpoint, and I'm going to begin to shade in the numbers that are greater than 2. So that goes, or excuse me, greater than negative 2, going in this direction. We'll come back to that in a minute. Now we're going to have x is less than or equal to 2. So again, we're looking at 2, positive 2 now. It can be equal to 2, so I'm going to have a solid endpoint. And x needs to be less than. In fact, it's going to be the shaded areas here. So these numbers from negative 2 all the way up to positive 2 are the intersection of these two inequalities. If we were just talking about one of these inequalities, like x is greater than or equal to negative 2, we would have shaded all the way over here to the arrow, right? And if we were looking at just less than or equal to 2, we would have shaded all the way over here to this arrow. But both of these have to be true. It said and. So only the part where both are true is the solution to this. You can also write these two inequalities together like this. And it says negative 2 is less than or equal to x, which is less than or equal to 2. Now this part, x less than or equal to 2, looks exactly like that, doesn't it? But this part looks like the opposite of that, right? It's reversed, x is on the other side, and the symbol has changed directions. We're going to talk about that in just a moment and explain why that is. There's another kind of compound inequality, and that's when the inequalities are joined together with the word or. And we consider those a union. So consider this example. We have x is less than negative 2, or x is greater than 2. Either one of these conditions can be true. So let's start here. X is less than negative 2. Well, it's not equal to negative 2, so I'm going to need an open endpoint, and it's less than. So I'm going to shade in going this direction. Now let's consider this side. X is greater than 2. Again, it can't be equal to, so I'm going to have an open endpoint. And this time my x's, my good values, if you will, are greater than 2. So they shade this way, going towards the arrow. So this is the solution, the whole solution. Any value that in the shaded in area, here or here, makes this union true. Solving inequalities. Solving an inequality with a variable is almost exactly like solving equations. Just like with equations, both sides of the inequality must always be treated the same. The goal is to isolate the variable by itself on one side of the inequality sign. As always, addition undoes subtraction, multiplication undoes division, and combining like terms is generally a good idea. There are two differences, though, and those are two situations where the direction of the inequality sign must be reversed. That means greater than would be changed to less than, or less than would be changed to greater than. The first situation is when we multiply or divide by a negative number. Here's an example of that. We know that negative 1 is greater than negative 3. We know that's true. Negative 1 is to the right of negative 3 on the number line. It's bigger. But when we divide both sides by negative 1, we get 1 and 3. And we have to reverse that to still make that true, because 1 is less than 3. It's to the left of it on the number line. The other situation when we have to change the direction of the sign is when we move the variable from one side to the other. So think of this. 5 is less than x. That means that there's some number that is where 5 is less than that. So the x's could be 6, 7, 8, 9, 10, right? 5 is less than those. Well, if we switch this around, we have to say that x is greater than 5 in order to be the same thing. Greater than 5, like 6, 7, 8, 9, 10. So let's do some examples of solving some inequalities. Here's an example that says x plus 7 is greater than 16. Alright, so we want to get x all by itself on one side, and 7 is being added, so we're going to subtract 7 from both sides, and we'll get x over here, and 16 minus 7 is 9. So x is greater than 9. That's the solution. We can put that on a number line. X is greater than 9. Here's 9. It can't be equal to, so I'm going to show an open circle. And it's greater than. It goes to the right, greater than. So we shade this part in. So any number that's bigger than 9 makes this true. So just like we checked our work when we solved equations, let's check our work here. I'm going to rewrite the inequality. I'm going to choose a number that's greater than 9. Let's try 10. So every time I see an x, I'm going to write 10. 10 plus 7 is 17. And that's true. 17 is greater than 16. So we got a true result, so our answer must be right. Here's another example of an inequality to solve. It says 14 minus 3x is less than or equal to 26. Our goal is to get x all by itself on this side of the equation. So let's start by getting rid of this 14 on this side. Let's subtract 14 from both sides. This cancels out, but remember that sign with the negative 3 didn't cancel out. It's just this that canceled out. So I bring down negative 3x. I bring down the sign. And 26 minus 14 is 12. Now x is being multiplied by negative 3, so I'm going to divide both sides by negative 3. That leaves me with x on this side, and 12 divided by negative 3 is a negative 4. 12 divided by 3 is 4. The signs are different, so the answer is negative. But now remember, I've got to switch this because I divided by a negative number. So the answer is x is greater than or equal to negative 4. Let's put it on the number line. Here's negative 4, and it can be equal to negative 4, so I have a solid endpoint. It's greater than or equal to that number, so I go to the right. The values are bigger. So there's my solution on a number line. And now to check our work, we can choose any number here that satisfies the solution. We can actually pick negative 4 because it's allowed to be equal to negative 4. So I will rewrite the problem. Every time I see an x, I'm going to write negative 4. Okay, multiplication first. Negative 3 times negative 4 is a positive 12. Negative times negative is positive. Now the addition. 14 plus 12 is 26. And is 26 less than or equal to 26? Well, it's obviously equal to 26. So my answer is true, and I've checked my work correctly.